go. We got a rectangular box that has a square base. So x and x, and then some height h. And it's supposed to have a volume of 100 cubic meters. So that's the 100 is equal to x squared h. All right, so we're trying to minimize the cost. So they tell us about the cost for the different places or different things has an open top, so no top. So the area of the base is x squared, and the cost of the base is $10. So 10 times x squared plus, the area of the sides are $5. So $5 times 4x h's. Okay, so let's see what this gives us. I get 20, equals plus 20xh. So I know, since I want the minimum cost, I'm thinking set the derivative of that equal to 0. So I know I'm going to need to solve this for h. So h is equal to 100 divided by x squared, and I'm going to substitute that in. So I get c equals 10x squared plus 20x times the h, which is 100 over x squared. Simplify before you take the derivative. So this gives me 2,000 over x. Now I'm ready to take the derivative. So it's all in one letter. So I get 20x minus 2,000 x to the negative 2. We want to set that equal to 0, right? And so if I set that equal to 0, I'm going to move this to the other side. So I get 20x equals, and at the same time I'm moving it to the other side, I'm going to put it in the denominator. So then I get x cubed is equal to 2,000 divided by 20, so that gives me 100. So x is equal to the cube root of 100. And since I've got this neatly written here, right, I know that I can just substitute that in. So I get h is equal to 100, and this is squared, right? So I'd have power over root and 100. So power of 2 over the root of 3. All right, so let's look at this one. Thrown down. So thrown down at 10 meters per second. So that means your initial velocity is negative 10. From 400 feet, that means your initial position is 400. Then I want to find out how fast it hits the ground. Since it's in meters, I know I'm using negative 9.8 for the acceleration of gravity. Sorry, let me make that a little neater. So acceleration of gravity is negative 9.8. Then if I make the velocity equation out of that, negative 9.8 t minus my initial velocity, and then put the last piece together to get my position function. So I'd have negative 4.9 t squared minus 10t plus 400. Okay, so what are they asking me for? How fast it hits the ground. So how fast is asking me for velocity, but wait, hits the ground, I need to find the time it hits the ground, and that's the time the position is equal to 0. Oh, you mean we have to factor that? No, we get to use the quadratic formula. I'll let you go do that, and I got the time about 8, and you're allowed to round about this. So that's the time, and so then the velocity it hits the ground is v of 8, which is negative 9.8 times 8 minus 10. And that would be the answer. That's the velocity it hits the ground. All right, so let me draw the picture in that I had like that. So here's 2 and here's negative 2. Okay, so again, I encourage you to start with the critical numbers. So I know the critical numbers where the derivative equals 0 are x equal negative 2 and 2. Before and after negative 2, I see that they're both negative, so nothing's happening there, right? Before and after 2, it's negative to positive. So at x equal 2, since y prime changes from negative to positive, I know that I have a local min. F of 2 is a local minimum. Okay, let's see what else I've got. So I'm just going to just start sketching that, right? So local minimum at 2. All right, so what else do I have going on here? So I know anytime the derivative graph is below the x-axis, right? If f prime is less than 0, that means f is decreasing. So let's just get a sense of what's going on. So it's decreasing to -2. Then it slopes 0. Then it's decreasing all the way to 2, right? So I'm going to maybe have to change that or change this. That's why you do this in pencil. And then after 2, it's increasing. Okay, so let me just fix this a bit. So it's decreasing, right? That's why you do this in pencil. Decreasing, slope 0 at -2. Decreasing all the way to 2. Doesn't matter that it's turning like that. That makes no difference for a max or a min. This is slope 0, kind of tangent line, right? Because that's where the derivative was equal to 0. And then after 2, it's increasing. So now we get the ups and downs, the basic shape. That's where you want to start. Okay, so then let's talk about the concavity. So you've got the basic idea. So let's look at here. So whenever f prime is increasing, that's here and here, right? That's when f double prime is positive, and that's where f is concave up. Concave up, so let's look at that, from -infinity to -2, and then from 0 to infinity. So -infinity to -2 is concave up, and then from 0 to infinity, it's cupped up, right? So this cupping is just enhancing the graph. So if I'm looking at where this graph, the derivative is increasing, that's where y double prime is bigger than 0. So that means y is cupped up. Oh, look at that. Y is cupped down, right? Second derivative less, hold on a second. Second derivative increasing, I just did that. Okay, so hold on. Sorry about that, made a mistake. Okay, here we go. Get back, okay. Here's our axis. So I did the increasing. Those are both cupped up. Okay, this part here is what I was trying to get to. So if f prime is decreasing, f double prime is less than 0, so that means f is concave down. Oh, look at that. That would make it cupped down there. So that makes a flat spot that's not a max or a min, all the way down and back up again.